Welcome, everybody. So let's start with this morning session. So Yassine, can you start recording and live streaming?
Yes, it's done.
Thank you. Thank you so much.
Good. Okay, thank you. So thank you, Francois, and so thank you all for coming. So welcome back to this now 5th session of this course on optimization for data science. So an update because so many people have requested this. So I've put the notes of the previous lectures online. So I've set it up on this webpage. So if you go to this URL, I've also put it on the chat. If you just go a bit on the top in the chat, you'll see a link to this URL. I've put the lectures for the first 2 days. So on Monday and Tuesday. And these are the annotated notes, the annotated together with the notes I put on my tablet. Okay, so so what I would like to talk about today. Okay, let's see how does it go. Maybe this. Yes, okay. So today what I will do is I will cover something, a very popular class of algorithms for optimization called proximal methods. So these have gained a lot of interest and traction in the last 20 years or so, motivated by some problems in statistics and in inverse problems and imaging. Particularly, one of the main motivations to develop these algorithms and to study them in detail was this lasso problem from statistics that I mentioned in the first lecture. This problem of finding solutions of linear systems that are sparse. And these problems involve a non-smooth regularization term, this L1 norm. And as well as other problems motivated from imaging, the problem of denoising and optimization problems involving something called the total variation regularization, which I'm going to talk about later on. Okay, so so just to recap kind of what we have seen in the last 2 days. So this is a very brief summary. So we looked, everything we looked at was mostly smooth optimization, and just yesterday afternoon we started looking at non-smooth problems. Okay, so if I recap what we did for smooth functions, we looked first at the gradient method, and we saw that if you want to, the gradient method has an iteration converges. After k iterations of the gradient method, the accuracy that you reach is L divided by k. Okay, so we said that this is a sublinear rate. And if you have if you have strong convexity as well, then the rate of convergence is 1 minus 1 over c to the power k. So here what I have put in this table is the number of iterations that you need to get accuracy epsilon. So that would be L over epsilon if you don't have any strong convexity, and that would be c log 1 over epsilon when c is the condition number. Okay. And then we've seen that the gradient method is not optimal, that you can do a simple modification to the gradient method to get much faster convergence. And this allows you to get L divided by square root of epsilon if you don't have strong convexity, and you get a square root of c log 1 over epsilon if you have strong convexity. And remember that the main idea behind this fast gradient method was to add a certain momentum term, or in other words, to use some of the previous iterations, some of the previous gradients that you had computed. So this is the situation for smooth problems. So yesterday I started talking about non-smooth problems. I introduced the notion of a subgradient of a convex function. Okay, so remember this is defined as any vector that allows you to get a global lower bound on your convex function. So it's defined by the inequality that f of y, so f of y is bigger than f of x plus g transpose y minus x. This has to hold for any x. Okay, so such a g is a subgradient of f at x. And so we define the subgradient method, a very simple method, which in the case of a smooth function just reduces to the gradient method. So where xk plus 1 is xk minus tk gk. And we have done some analysis of this method, and the conclusion was that this is a relatively that the convergence of this method is not very good. I mean, to have convergence, you essentially have to tune the step size in a certain way so that it is decreasing. So it has to decrease with the speed of 1 over square root of k. And in this case, you get convergence, but if you have constant step size in general, you do not have convergence, but you just have, you converge to a neighborhood of the optimal point, and then you keep oscillating around this neighborhood. Okay, and I showed some numerical experiments that demonstrate this behavior. Okay, but also if you have convergence, if you happen to choose the step size in the way I said, so 1 over square root of k, then we saw that the convergence, that f best k minus f star, so this is the best iteration, the best function value that you get up to iteration k minus the optimal value. We said that this is roughly less than g times the norm of x0 minus x star squared divided by square root of k, or sorry, divided by k squared. Sorry, divided by square root of k, yes. So, so what this means, if I want to reach accuracy epsilon, okay, so to reach accuracy epsilon, this tells me that, again, if I forget about this norm of x0 minus x star squared, this tells me that I need g divided by epsilon squared iterations to reach accuracy epsilon. Okay, and you can see that this is much worse than what we have in the smooth case. So in the smooth case, for the gradient method, we had L over epsilon, and the fast gradient method, we have L over square root of epsilon. So, so again, this is a much worse convergence, and this is again something that we observe in practice, that the subgradient method is a method that is very slow in general. So, so again, so what I'm going to do today, again, is to explain these faster alternatives to the subgradient method. So these are methods that are especially adapted for problems that have a specific structure, a specific, what we call a splitting structure. So these are problems where you want to minimize a certain function, and this function can be written as a summation of two relatively simple functions. The first one is smooth, and the second one is non-smooth, but is relatively simple. And this fits exactly the case of the lasso problem, where you want to minimize an L2 norm squared plus an L1 norm, and an L1 norm is a relatively simple function. Okay. Yes. So this is what I'm going to talk about today, and we'll see that the convergence rate that we get is going to match essentially the convergence rates of smooth problems. Okay, so really the non-smoothness will not affect the convergence rates at all. We'll be able to develop a proximal gradient method which will converge like L over epsilon, and a fast proximal gradient method that will converge like L divided by square root of epsilon. So very fast rates. Compared to just applying a standard subgradient method without looking into the structure of the problem. Okay, so and these are really the methods of choice to solve these problems in statistics, like the lasso problem and problems in inverse problems like denoising problem and so on in imaging. I will show some examples at the end. So so let me yeah, so really in this session, you really want to have in mind this lasso problem, so that's why I rewrote it here. The problem is to minimize over x in Rn a certain squared loss term, so norm of ax minus b squared, plus what we call a regularization term, lambda times the L1 norm of x. Okay, and the L1 norm is obviously the sum of the absolute values of the components. That's a non-smooth term. Okay, so that's why I cannot directly apply the gradient method to this optimization problem. Okay, so so as I mentioned in the first session, in the lasso problem, the situation is usually that A is actually underdetermined, so meaning that M is less than N. Okay. Okay, and so when M is less than N, in fact, the first term is always smooth. Okay, and we saw that if I call g of x to be the norm of ax minus b squared, Okay, we've seen that the gradient of G of X is A transpose AX minus B with a 2. And so the Hessian of G of X is just 2A transpose A. Okay, so if A, the general case in underdetermined systems, so in the Lasso case, is usually that A is actually a matrix that looks like this. So it's a rectangular matrix where M is less than N. Okay, so this means that the Hessian of G of X, okay, is a matrix product, so it's a tall matrix by its transpose. Okay, and so by simple linear algebra, such a matrix that's a big, it has the big dimensions. Okay, so it's an n by n matrix. Okay, but it has, it will be rank deficient. Okay, so many of the eigenvalues of the Hessian will actually be equal to 0. So this means that the first term in the Lasso case will usually be smooth but not strongly convex. Okay. I mean, this is just a kind of a remark in passing. But our algorithms will apply just as well for the strongly convex case, and in the case of strongly convex functions, we'll be able to get the faster linear convergence rate. Okay, so so let's now introduce the main character of this algorithm, of the new algorithm that I will be presenting, which is the proximal operator. So this is a kind of a mathematical definition I have to do, and we're going to study this operator quite a bit before introducing the algorithm, the proximal gradient method. Okay, so this is really a key definition. So if H is a convex function, I define the proximal operator of H to be this mapping. So so note that this is a mapping that takes a vector X in Rn and that outputs also a vector in Rn. Okay, so prox, so I can write here that prox H, okay, is a mapping that goes from Rn to Rn. Okay, I'm assuming here that H is a function defined on Rn. Okay, so the proximal operator is defined as follows. So the input is X, and what you do, the output of prox is actually the solution of an optimization problem. So it is the argmin over U in the domain of H of U plus a certain quadratic term, which is here in 1/2 of norm of U minus X squared. Okay, so essentially, if you want, is that you take H and you add a certain if you want a squared regularization term, so that you don't get very far from X, from the input point X. Okay, so 1/2 this term, 1/2 of norm of U minus X squared will penalize having U very far from X. Okay, so it's kind of a trade-off between you want to minimize H, but you also don't want to be very far from X. Okay, so now the first kind of question that one can ask about this proximal operator is it well defined? Because I have an argmin here. Okay, so is this argmin actually, does this argmin consist of a unique point? The answer is yes. So this is well defined because the function U plus 1/2 norm of U minus X squared, okay, this function is strongly convex. It's strongly convex, and so has a unique minimum. Okay, so has a unique minimizer. Okay. So remember, whenever I have a strongly convex function, remember that the function is always lower bounded by a convex quadratic, okay, a non-degenerate convex quadratic. So it cannot have two minimum. Okay, obviously it can have only one minimum. So so this means that that this prox function is well defined. Okay. So okay, I mentioned this before, that computing the prox function itself is a convex optimization problem. Okay, but we will see that for some special functions, this convex optimization problem has a closed form solution. Okay, and the particular case of the L1 norm will be the case of that we will study in this session. But I mean, it's not the only possible case. Okay. So, and this is the problems of interest for which the proximal gradient method will apply is problems where you have a regularization term where the prox function can be computed easily, or the prox operator has a closed form solution, or at least can be computed in an easy way. Okay, so also note that if I take h of c, so h of x, the function h to be the indicator function of a convex set, okay, and the indicator function in convex analysis is not defined to be 1 or 0, but is defined to be 0 and plus infinity. So it's 0 on the convex set, and it's plus infinity otherwise, okay? This is so that the indicator function of a convex set is convex, in the way it's the reason the way it's defined in this way. Then you can see that if h is the indicator function of a convex set C, then the prox of such an indicator function is just the projection on the convex set C. Okay, because in this case I can write that prox. So I have IC of x. Okay, it's just the argmin. Okay, of u. Okay, so actually of u in C. Of this is h of u is just equal to 0 on C. So this is just 1/2 of the norm of u minus x squared. Okay, so what I want to do, so this is the projection. So you want to find the closest point to x in the convex set C. This is a picture I drew already. So you have a convex set, okay, and you have a point x. So you project your point x on the convex set C. Okay, so this is what I call pi c of x. It is the projection of C of x on the convex set C. Okay, so now, so we've seen the definition of the prox operator. It's a well-defined operator, and if you want, it generalizes. It in the case of the indicator function of a convex set, it just reduces to the projection operator on the convex set. In fact, the prox operator, if you want, is a functional generalization of this notion of projection on a convex set. So. Okay, so let's now. I want to, prove a very simple proposition that characterizes the proximal operator, and this will be useful just to carry out the examples that I will do later on. Okay, it will just simplify some of the calculations I do. Okay, so so let's prove this. So the claim is that the prox of h at x is equal to u if and only if x minus u belongs to the subdifferential of h at u. So remember, this is the subdifferential of h at u. Okay, so this is really a one-liner. So so the prox of h at x. Remember, this is the argmin of h of u plus 1/2 norm of u minus x. The argmin over u. Okay, so if I call, okay, I should probably use different letters. Let me just use u tilde here. Okay, so if u is the prox at x of h, okay, then the optimality condition of a convex optimization problem I mentioned last time is that 0 has to belong to the subdifferential of the function I'm minimizing. Okay, so if I call this function phi of u tilde, okay, then what I must have is 0 has to belong to the subdifferential of phi at u. Okay, but by the calculus rules I mentioned yesterday for the subdifferential, okay, this is equal to the subdifferential of phi at u, of h at u, okay, plus the gradient of this quadratic term at u. I mean, this is a smooth function, so it has a gradient. So, but the gradient is very easy to compute. It's just actually u minus x. Okay, so I have that 0 has to belong to dh u plus u minus x. okay, which is equivalent to x minus u has to belong to the h of u. Okay, which is what I wrote, which is what I have in at the top here. Okay, so okay, so it's really a very simple proof. It's just really writing gradient or zero belongs to the subdifferential and just rearrange it. But this will be quite useful. So to do some computations. Okay, so now that we've introduced the prox and seen a characterization of what the prox means, let us now see the simplest example of the prox operator in action. Okay, before I do so, let me just have a very useful property that is, again, very easy to establish. And that is the prox of what we call separable functions. Okay, so what's a separable function? So a separable function is exactly what you see on this slide. Okay, so it's a function that you can write as a summation of functions that only depend on one component. So meaning h of x is the sum of hi xi. So so you have the way the function depends on x1 is just through this function h1. So it's really a sum of functions of a single variable. Okay. Then in this case, the prox of h has a very simple. It decomposes very simply because you just have to compute the prox of one-dimensional functions. Okay, and this makes again things much easier. So let me just justify this claim. Again, it's very simple because the prox of h at x again is the argmin over u of h of u plus 1/2 norm of u minus x squared. Okay, so now I'm going to write this. This is the argmin over u of the sum of hi of ui. Okay, plus I'm going to write this square L2 norm into a sum of ui minus xi squared. So this is plus 1/2 of ui minus xi squared. Okay, this is the summation from I equal 1 to n. Okay, so note that I'm now minimizing as a sum of functions, but the functions are completely decoupled. Okay, the functions are completely decoupled. And so this means that I can minimize individually u1, u2, u3 up to un. Okay. Obviously, the minimum of a sum of two functions is not the minimum of the one plus the minimum of the other one, because you will in general have coupling. But if the functions are completely decoupled, then you can indeed minimize over the first one and and then minimize over the second one. Okay, so this is really okay. So here the problems are decoupled. Okay, okay, so this is really equal to you can see right away that this is going to be equal to the prox of the first applied to x1, and then prox hn applied to xn. Okay, because essentially the u1 is going to be equal to the argmin. So in general here, ui is going to be equal to the argmin. So over u tilde, right? So of hi of ui tilde plus 1/2 of ui tilde minus xi squared. Okay, where ui here is the ith component of the prox operator. So that's why we have this decoupling. Okay, so it's very easy. There is no no complications, no difficulty really here. So okay, so this is and again, if we think ahead about the L1 norm, the L1 norm is a function that is separable because it's the sum of absolute values of xi. So it really separates along the components of x. So so let's now do some computation. So let's look at the absolute value function. Okay, or rather, actually, let me look at the scaled absolute value function. So just lambda times the absolute value function. So this is a function from R to R. Okay, so it's a one-dimensional function. So so let's do the computation of the prox operator. So the prox, okay, of h at x is the argmin of then lambda absolute value of x plus 1/2 u minus x squared. Okay, this is the argmin over u. Okay, and then I can take the lambda. I'm just going to move it. I'm just going to divide. So this is the same as absolute value of x plus 1/2 lambda u minus x squared. Remember, I'm taking here the argmin, so it doesn't really matter if I scale the function I'm minimizing. Okay, this is, and here lambda is positive. Okay, so now remember the necessary and sufficient condition for the prox that we derived. So what I want is that x minus u has to belong to the subdifferential of h at u. Okay, so we have computed the subdifferential of h at u yesterday. We have computed the subdifferential of the absolute value function, and we know so from yesterday. We know that the subdifferential of h at u, remember, this is equal to plus lambda if u is positive. This is equal to minus lambda lambda, the interval minus lambda lambda if u is equal to 0. Okay, and this is equal to negative lambda if u is negative. Okay. So now if I want to compute the prox operator of the absolute value function at a certain x, okay, I'm going to have different conditions, okay, depending on whether u is going to be positive, 0, or negative. So obviously u is the thing I'm trying to find, okay, but I'm just going to do this case-by-case analysis for my reasoning, and then we will be able to just give the solution and verify that the sufficient conditions are actually satisfied. Okay, so case 1. Okay, if u is positive, okay, so this means then that x minus u has to be equal to plus lambda. Okay, and so x minus u is equal to plus lambda. This means that u is equal to x minus lambda. And again, because I'm in the case u is positive, then this means that x minus lambda has to be positive. Okay. So I mean, to kind of go backwards, then if x minus lambda is positive, if I set u to be x minus lambda, then this is going to satisfy the sufficient conditions of optimality, and this is then going to be equal to my prox function. Okay. So so then case 2, I'm going to summarize this at the end. So case 2, if u is negative, okay, then this means that x minus u has to be equal to negative lambda, because in this case, dh of u is equal to minus lambda. And so this means then that u is equal to x plus lambda, and this has to be negative. Okay, because this is the case I'm in. And finally, the last case is case 3. U is equal to 0. So in this case, x minus u has to belong to minus lambda lambda. Okay, but u is equal to 0, that's the case I'm in. Okay, so i.e., so here this means that x has to be between minus lambda and lambda. Okay, so this covers all possible cases. Okay, so so again, to kind of recap, now if x minus lambda, so x is the input that you give me, and I'm trying to compute the prox operator at x. If x is bigger than lambda, then by setting u to be x minus lambda, I have that the condition x minus u belongs to the subdifferential of h at u, and so I know that this u is the value of my prox at x. Okay. And the same for the other cases. So if I kind of summarize, if I summarize what the prox operator of lambda times the absolute value at x, okay, so you will see that this is equal to x minus lambda if x is bigger than lambda. Okay, it's equal to x plus lambda if x is smaller than lambda, and it is equal to 0 if x belongs to minus lambda lambda. Okay, so this is exactly what I have shown in this case by case analysis here. Okay, so now we can plot this function. Okay, so okay, let me use a different color here. Okay, so I have I have lambda and minus lambda. Okay, in between minus lambda and lambda, the function is equal to 0. This is what I have here. And for lambda, for x bigger than lambda, I have a straight line. Okay, so this is my function. And then for x smaller than lambda, I have a straight line as well. Okay, so this is really my prox operator of lambda absolute value of x. Okay, and this is okay, very well known in statistics. This is an operator that's very well known. It's called the soft thresholding operator. Okay, because it is some kind of a thresholding operator, but it is soft because you just reduce the value. If you're bigger than some threshold, you kind of decrease the value of your input by that threshold parameter lambda. Okay. So okay, so we have computed then the prox operator for the absolute value function. So now what I want to do is what is the prox operator for the L1 function? So now if h of x is the L1 norm, or rather lambda times the L1 norm of x, so that is the sum from I equals 1 to n of xi, and I have a lambda here. Okay, so so we can use the fact that this function, this is separable. Okay, and so this means that the prox at h of so at x of h is equal then to what I'm going to denote here, s lambda of x1 and s lambda of xn. Okay, where s lambda is the soft thresholding operator. Okay, and so so meaning that s lambda of x is just what we computed is the prox lambda at x. And so this is equal to x minus lambda if x is bigger than lambda, x plus lambda if x is smaller than minus lambda, and 0 if x is in minus lambda lambda. Okay. Okay, let me check it. Yes, so I forgot a negative lambda. Okay. So this is the prox function of the L1 norm. And so we see that the L1 norm has a simple prox function that this is very easy to compute essentially, to compute the prox operator of the L1 norm. Okay, so now now I'm in shape to state what the proximal gradient method is. Okay, so the proximal gradient method is it's an algorithm that applies to the optimization of any function of the form g of x plus h of x. Okay, so I want to minimize a function f that can be split into two terms. G is a smooth term and h is a non-smooth term, but it's a simple non-smooth term that has, and the definition, what does it mean to be simple, or kind of the notion here means that h has a simple prox, a prox function that you can compute easily, something like the L1 norm, for example. Okay, and so what is the proximal gradient method has also a very simple definition. So it's as follows. So you start from starting from an initial point x0, you iterate by the following rule. So xk plus 1. So you first take a gradient step along G. So G is smooth, so that's fine. So xk minus tk gk, that minus tk times the gradient of gk, of G, sorry, at xk. And then you take a proximal, you apply the proximal operator to this step. Okay, so you take a gradient step along G, okay, as if there was no H. And then the H will appear by doing a proximal operator on this gradient iteration. Okay, so I mentioned before that if H is the indicator function of a convex set C, then the prox operator is the projection operator on that convex set. Okay, so in this case, the proximal gradient method just reduces to the projected gradient method. Okay, so the projected gradient method is you want to minimize a function on a convex set. And so what you do is that you have a certain x naught, okay, you move along the gradient, okay, so, and then you project this iterate on the convex set. And then let's say you move along the gradient, and then you project on the convex set, and so on. Okay, I've already mentioned this in the first session. And so this projected gradient method is a special case of the proximal gradient method when H is the indicator function. But obviously another important application is exactly when G is the norm of AX minus B squared, and when H is the L1 norm. Because in this case, the prox function I can compute easily. So this does apply to the lasso problem. Okay. And so what is nice, I mean, again, this algorithm is very simple to state. Okay, so what about the convergence of this algorithm? So so the convergence is identical. The results we have are identical to the gradient method. So so if G is M strongly convex and L smooth, okay, then you can show that the iterates converge linearly to the optimal point. Okay, and the linear convergence rate is roughly 1 minus 1 over C to the power K, where C is the condition number of G, so it's L over M. And if G is convex and L smooth, without assuming any strong convexity, then you have a sublinear convergence rate like 1 over K. Okay, so it's really identical to what we have already proved for the gradient method. Okay, and I note that this is much better. These complexity iterations are much better than the subgradient method that we saw last time. Okay. So okay, so I wanted to kind of maybe say a few words about the proof. So I will not do the full proof, but rather I will just say kind of a few words just to give you an idea, and then in the you can probably look up more details of the proof at some of the notes some of the references I put on the web page. Okay, so let me say a few words here. So the idea really, so xk plus 1, the iterate is defined as the prox of tk h times, applied to x minus xk minus tk gradient of g at xk. Okay, and the step size that I'm going to look at, and the choice of step size follows exactly the same rules as for the gradient method. So in this case, I'm just going to look at tk is equal to 1 over L, so the constant step size. So that's the prox of 1 over L times h of xk minus 1 over L gradient of g at xk. Okay, so here this is constant step size. Tk is equal to 1 over L, where L again is the smoothness parameter of G. Okay, so for the analysis, it is useful to be able to write this iteration rule just like what we had for the gradient. So I want to be able to write this as xk minus 1 over L times G at xk. Okay, where G is not the gradient, but if you want, it's a pseudo gradient. It is essentially G is defined by this equality exactly. And so you can see that G of xk, if you just do the math, you have to get that G of xk is equal to L times xk minus the prox 1 over LH of xk minus 1 over L gradient of G at xk. Okay, so okay, so with, and now the question, now having done this definition, now we focus on the properties of this mapping big G. Okay, and kind of the main lemma, so the key lemma, so key lemma in the analysis of this method is to show something along the lines of what we have shown in the gradient method when we did not have any prox term, is to show really that f at xk plus 1. So here f is the summation of g and h, by the way. So f of x, let me write here maybe. So f of x is equal to g of x plus h of x. That's really the function I'm trying to minimize. Okay. So, and I want to understand how does this function f decreases. So f of xk plus 1, okay, the key lemma is that for all z, okay, f of xk plus 1 is less than f of z plus g of xk transpose xk minus z. Okay, minus 1 over 2L times the norm of g of xk squared. Okay. Okay, so this is really the key lemma that one has to prove to establish this result. So I will not prove this key lemma, but I'll just see one of the consequences of this key lemma and just what are the main ingredients to prove it. But I will not do the technical derivations. Okay, but the main consequences are as follows. So consequence 1. Okay, is that if you choose, so you're free to pick z whatever you want in here. So if you choose z to be just xk, okay, this is the previous iterate, okay, then what you get is that f of xk plus 1 is less than f of xk minus 1 over 2L times the norm of g of xk squared. Okay, so this should remind you of one of the steps that we had in the proof of the gradient method. So so this is this tells us essentially that this is a descent method. Okay, so okay, meaning that the function values actually do decrease from one iteration to the next. And the second consequence, so consequence 2, then this is how you actually go on with proving convergence, is you choose, so pick z to be x star, the minimizer of my function, which I assume exists. Okay, so what you have is that f of xk plus 1 is less than f star plus g of xk transpose xk minus x star minus 1 over 2L norm of g of xk squared. Okay. And just for convenience, let me rewrite this as f of xk plus 1 minus f star is less than this. Okay. And then now what you can do is that you can show that this is going to be equal to 1 over 2L times the norm of xk plus 1 minus x star squared minus the norm of xk minus x star squared. Okay, and here to go from here to there, what this involves is you use the fact that xk plus 1 is equal to xk minus 1 over lg of xk. Okay, and use the completion of squares. So this thing that we used also in the analysis of the gradient method, that you use that the norm of a squared minus 2a transpose b, okay, that this is the norm of a minus b squared minus the norm of b squared. Okay, and then from the inequality above, if you sum it up, so from the inequality above, okay, and then so, or rather maybe summing the inequality above, I would say. Okay, what you get is something like the sum from I equals 0 to k. So here I would say like 2L times f of xi plus 1 minus f star. Okay, this is less than the norm of xi plus 1 minus x star squared minus the norm of xi minus x star. It's less than the sum from I equals 0 to k minus 1. Okay, so what you get is you get a telescoping sum in here. And then you can essentially finish the proof from here, and the rest is very similar to what we have done for the gradient method. Okay, so I will not finish the proof, and you use the fact also that this is a descent method to bound the left hand side by f of xk plus 1 minus f star. Okay, so now really we see that the key lemma is really this fact here, this inequality. Okay, so maybe let me just say a few words where this inequality comes from. How do you actually prove it? So really, the proof of this inequality comes, so you use obviously the L smoothness of the function little g, and then you use the fact that we're using the prox operator somewhere. Okay, so okay, let me just say ingredients to prove the key lemma. Okay, so obviously you have to use that G is L smooth. Okay, so remember that if G is L smooth, then you have a quadratic upper bound on G. Okay, and you use the fact that so remember that G of x was L times x minus the prox of 1 over LH of x minus 1 over L gradient of G at x. Okay, so by the definition of prox operator, or rather by this sufficient condition that I mentioned last time involving the subdifferential, what I know is that x minus 1 over L gradient of G at x, which is this term that you see here. Okay, so remember that I could call this the U, remember from the previous notation. Or rather, sorry, this is not the U. The U is the whole thing. Okay, the U was actually this whole thing. So this minus the U, so minus the prox 1 over LH of blah, blah, blah. Okay, but this has to belong to the subdifferential of 1 over LH, okay, applied to x minus 1 over L gradient of G at x. Okay, so this is kind of a complicated thing, but I can, if I multiply by L, okay, if I simplify this condition, this actually has a simple rewriting in terms of big G of x. So this is just telling me that, in fact, what I have is that, so big G of x minus the gradient of G at x belongs to the subdifferential of h at x minus 1 over L gradient of G at x. Okay, so if you combine these two ingredients, so A here and B, and this essentially I can write this is the B here. Okay, then if you combine in the right way these two ingredients, then you can prove this inequality in the key lemma. Okay. So I'm not going to do it. So yes. The proof is elementary. I don't say it's easy, but it is elementary. It just uses basic inequalities of convex functions. So, okay. So now let's go back to the lasso problem. So I want to minimize, again, the norm, 1/2 of the norm of ex minus b squared plus a regularization term, lambda times L1 norm. Now, I mentioned that the first term, the smooth term, has a Lipschitz, is L smooth, with L being the lambda max of A transpose A. So here there should be a 1/2. Okay, and the second term, the regularization term, has a simple prox function that we already derived, which is the soft thresholding operator. Okay, so the resulting algorithm, the xk plus 1 is equal to, so the soft thresholding operator of lambda tk L1 norm applied to xk minus, now I have a tk A transpose A xk minus b. Okay, so now remember, so this is the gradient of g at xk. Okay, this is my g of x. This is my h of x. Okay, so this is the gradient of g at xk. I have a step size, and this is S is the soft thresholding. S is the soft thresholding operator. Okay, it is the prox of the L1 norm. Okay, so this algorithm is very well known in computation statistics, if you want, and it is known by the initials ISTA, so for iterative soft thresholding algorithm. Okay. And it was derived by, different people in different ways and so on. So now, okay, so this is the proximal gradient method, which leads to this ISTA algorithm in the case of squared loss and L1 norm. The framework of, what I've presented before, you can actually apply, you can actually define what we call a fast proximal gradient method. So it's exactly the same as the proximal gradient method, except that you use this momentum term that we mentioned last time, or the Nesterov's fast gradient method. And this gives you just a slight modification on this proximal gradient method, where again you take, remember you define this auxiliary sequence y, which is an extrapolation of xk. So remember I had xk minus 1 xk, and we said that the way fast gradient methods are defined is that you first extrapolate xk in the direction of the previous iteration. Okay, so you move to a certain point y. You don't really move to y, but what you do is that you query the gradient of your function at y, and then you move from xk to xk plus 1. This is then your new iterate. Okay? And then you actually move in there. So you do exactly the same thing in here, and then you take the proximal operator at the end. Okay, this is known, again, in the case of the L1 norm, or H is the L1 norm and G is the squared loss. This is known as the fast iterative soft thresholding algorithm with the initials FISTA. Okay, and again, this is a very popular algorithm in statistics and inverse problems. If you just Google FISTA and ISTA, you will see that these papers have many, many citations and are very well known. So one can prove that, I did not write it here, but the convergence, so this algorithm convergence, so if G is L smooth, okay, what you get is f of xk minus f star is less than roughly, so L divided by k squared times the norm of x0 minus x star. Okay, so you get a convergence rate in k squared, which is faster than the proximal gradient method. That's why it's called the fast iterative soft thresholding algorithm. Okay, so now let me conclude by a simple numerical experiment. So this is this lasso problem I mentioned with, okay, these are moderate problem dimensions. So 300, A is a matrix of size 300 by 600. And now in red is, this is the proximal gradient method. Okay, and in blue, this is the fast proximal gradient method. So this is the fast proximal gradient method. So this is Fista. Okay, and this is what was called ISTA. So, okay, so you can see that both of them do converge. We don't have linear convergence rate because I'm not strongly convex. Okay, because I'm in the underdetermined case. So I mentioned, as I mentioned before, that A transpose A is a rank deficient matrix. So it has many zero eigenvalues. So it's not strongly convex. So I don't see this linear convergence rate. But we still observe convergence, and we observe also that the fast proximal gradient method is much faster. Okay, and we also, another thing that we see is that the fast proximal gradient method is not a monotone function. Is not okay. So it has some ripples. This is a well-known observed effect of this fast this Nesterov's fast gradient methods. Okay, and it's not a descent direction in the sense that the value of f can increase and then decrease again and so on. Okay, it does not decrease monotonically. Okay, so okay, so I just have two more things I wanted to say before I conclude this morning session. So this is kind of something that just to consider, and because this has a name, it's kind of fairly well known in optimization. One can think about applying the proximal gradient method when the function g is equal to 0. Okay, so if let's say I want to just minimize. If I go back to my slide in here, I want to minimize a function h of x, a convex function h of x. Let's forget about the requirement that h has a simple prox. The algorithm is well defined when, even if h does not have a simple prox. I just want to minimize the function h of x. So if I apply the proximal gradient method and I take g to be 0, then the iterations I get are just xk plus 1 is the prox of xk, and the prox is taken with respect to tk times h, where tk is the step size. So okay, so this is known in the literature as the proximal point method. Okay, it's a method that is it is hard to argue. It is not in general, it's not a practical algorithm, because if the goal in the first place is to minimize h, here each step in the proximal gradient method involves actually minimizing the function h plus a certain quadratic term. Okay, so the only reason one would consider such a method in practice is if minimizing the function plus a quadratic term is easier than minimizing the function h of x directly. Okay, and one reason this could be easier is because the function h plus a quadratic term is a strongly convex function, whereas the function h in general is not going to be strongly convex in general. Okay, so the idea here would be to leverage the strong convexity of this of h plus 1/2 of norm of x minus xk to that would make the minimizations in each iteration easier than the global optimization, the global minimization of h. Okay. But besides being kind of, from the practical point of view, I would say it's not used very much, but it is of theoretical and conceptual interest, this algorithm, kind of to, yes. So the last thing I want to mention, yes, is the limitations of the proximal gradient method. Okay, from the practical point of view, so it is a very good algorithm whenever your function, your regularization term has a simple prox. But in some applications, actually, this is not the case. And in some very common applications, the regularization term does not have a simple closed form prox function. And maybe the simplest example is whenever you have an L1 norm, but the L1 norm is composed with a linear, the L1 norm is applied to a linear function of x. So for example, you want to, let's say that you want to minimize the norm of ax minus b squared, but what you want, the thing that you want to be sparse is not directly the components of x, but you want the components of x in a different basis to be sparse. Okay, let's say in a wavelet basis or in some Fourier basis, you want them to be sparse, okay? And so this immediately destroys the separability, the separable structure of the L1 norm, and the prox function is no longer easy to minimize. Okay, this is because the L1 norm of dx is not separable anymore. Okay, so so one application I mentioned is if you want your vector that you want to reconstruct, if you want it to be sparse in some different basis than the canonical basis, I mentioned the wavelet basis. Another very well-known example is in denoising. So the problem in denoising is as follows: you're given an image that is noisy and you want to denoise it. So on the left, this is what you have as input, and on the right is what you hope to recover, the original image. So one approach that is based on optimization and that is extremely popular in image processing is the so-called ROF model, the Rudin-Osher-Fatemi model. And it is based on so your estimate x hat, if you want, is the argmin of this. So what you do is you take B is your noisy image. Okay, so you minimize norm of x minus b squared plus a certain regularization term, and the regularization term here is called the total variation. This is called the total variation. Okay, it's an L1 norm, but an L1 norm of some finite differences of the pixel values. Okay, so you form for each pixel value, you form a sort of derivative, and then you take the L1 norm of this. And the effect of this regularization is that the resulting image x hat that you will recover will tend to have piecewise constant areas. And the effect is that it will remove this noise that you can see on the left image. Okay, so this problem, even though it has the form of a smooth plus an L1 norm, the L1 norm here is composed with a certain function, and so the prox function of this total variation term is not simple. And so one needs kind of different tools to be able to deal with such a problem. And so this is exactly what I will talk about this afternoon. I will see how one can use duality, leverage duality to actually deal with such problems and be able to apply these projected gradient methods and proximal gradient methods to these problems. The whole idea will be to decouple to essentially, if you want to introduce a new variable y, which plays the role of d times x or g of x here, and this will allow me to decouple the two terms. Okay, and then by applying a projected gradient method on the dual, this will allow me to resolve the problem essentially. Okay, but this is something I will talk about this afternoon, and so this afternoon topic will be on duality. So I will stop here and can have a look at the questions if there are any.
Thank you. Are there any questions?
So let's see chat. So okay, so someone was saying lambda times absolute value of u, but I don't know if that's a question or a comment more.
I think this was a long time ago. I think so.
Oh, I see. Yeah, that was at 9:30. So let's yeah. So maybe let's wait a bit for if anyone has a question, you can put in the chat.
So there is one question.
Oh, can you give us an example where the prox gradient method is easier than the minimization of objective function directly? Okay, so the goal here is that I cannot. I'm trying to find a method that can minimize this. Let's say the squared loss plus the L1 norm. Okay, and among the methods that we have seen, kind of the gradient method the gradient method and the fast gradient method, these methods do not apply because I have a non-smooth term. Okay, so I cannot apply the gradient method. One could apply the subgradient method, but we saw last time that the subgradient method is pretty slow. So the goal of today's lecture was to show a method, this proximal gradient method, that is well suited to this such a problem with a splitting structure. Okay, so so yes, and this is actually the method of choice, this proximal gradient method, and particularly the fast version that people do use in practice. Yes, so I hope. I mean, I hope that answers your question, but yeah. Okay. Okay, what about the complexity of the proximal point method? Yes, okay, so I have two questions. So, okay, the proximal point method does converge, I mean, if the, does converge like 1 over k. Okay, this is the convergence that that is known. And okay, so someone is asking if the non-smooth term is very complicated, are there other methods to apply? Yes, so this is, okay, if the non-smooth term is extremely complicated, you can always apply the subgradient method. So this is always a method to do. What I will show this afternoon is a way to get around essentially applying the subgradient method. And exactly, I mean, such problems where you want to minimize an L2 norm plus an L1 norm, but apply it to a linear function of x. These are the proximal gradient method is not directly applicable, but we will see some other method for which this is also applicable. And maybe I should also mention, going ahead, that tomorrow what I will do is that I will show that actually many of these methods, many of these problems, I mean, let's say this last two problem, but I will talk about tomorrow.
I think there was a cut in the sound. So maybe
okay.
if you could repeat, this would be
okay. Can you hear me now? Is it?
Yeah. No, that's fine.
Okay, I see. Yeah. So yes. Okay, I will repeat now. So yeah. So I was saying that if the non-smooth term is complicated, you can always apply the subgradient method. Okay. For certain. Okay, if the non-smooth term is very simple, like has a simple prox function, you can apply the proximal gradient method. Later today, I will explain how you can get around, still apply some kind of proximal gradient method by using duality, so to handle a bit more complicated non-smooth terms. Okay, and what I also mentioned is that these problems involving a non-smooth terms, can also sometimes be reformulated as linear programs or as quadratic programs by, adding these L1 terms in the constraints and so on. I will explain these operations tomorrow. And then you can use standard algorithms for linear programming and quadratic programming to handle these problems. This is something I will explain tomorrow, how to, when I talk about structured optimization problems, these are linear programming, quadratic programming, and semi-definite programming. Okay, so we can apply the proxy on a convex constraint problem. Yes, yeah. I mean so if your problem is constrained, I mean, you can apply this projected gradient method. Okay. So yes, I mean, in this case, the prox. I mean, if you put the constraint as an indicator function. As an indicator function, then this will essentially be just a projected gradient method. So that Okay, let's see. Effect of parameter bk. I don't know what is. I don't think I had any bk. So. Okay, what if the objective function I want to minimize is an integral? I don't know. I mean, that's. I mean, so here I presented thing from an abstract point of view. I mean, I just want that f is a convex function, okay, that or g is a smooth convex function, h is a possibly non-smooth convex function. Then it's given as an integral. It's given in whatever way that you want. But the only thing I need to be able to do is I need to be able to compute the gradient of g of the smooth term. If you can compute the gradient of this function that's given as an integral, then that's good. And I want to be able to compute the prox of h. That's the only thing I need to be able to run this algorithm. Other than that, if the function is given, I mean, it could be given in whatever way that you want. That doesn't really matter. Okay. Okay, it seems that's
no more questions.
yeah, it seems there are no more questions.
So if there is no question, thank you, Hamza, for this all these very nice lectures. So we resume in the afternoon. Let me check the schedule, but I guess that you know this.
Mm-hmm.
You know this. So let me check from the email I have. So this should be 2 p.m. I think.
Yes, yeah, that's right. Yes, yeah. So in the same Zoom Zoom link.
Zoom link, absolutely.
Yes. Okay. So
thank
you everyone, and I'll see you this afternoon then. Okay. Bye-bye.
Bye-bye. Thank you.
Thank you. Bye-bye.